So today what we're trying to do is trying to model truss structures like this, and then showing on the screen, and then with the top core, and then a slightly larger member, and the bottom core the same size, and the middle layer a smaller size, and then all this structure was simply supported by bin structures at the bottom corner, and then the top core subject to a subject to a point load uh, acting on the each node on the top core, and then the edge, because is half of the distance that of the other middle one, so you got half of the loading applied to the edge one. So we're trying to model is a simple structure we've done already. So I don't think it's a big issue that to model this structure. But more importantly, in this afternoon, oh no, so not afternoon, in today, depends on when you listen to this video. And then and this time what we're trying to do is that we're trying to say, for example, if you get a client who want to open up his maybe living room to create an open living space, or maybe shopping mall want to take off this column to create a large opening, then you need to put a I bin under it. So you put a sorry, not I bin, you put a bin. So not necessarily to be I bin, you put a bin under it to support these structures to create a large open. And then but what you require to do is that you create the beam which have the same stiffness, same support stiffness as the column provide to the truss. Say for example, how much loading apply in here, this structure move down a certain distance, you require the new beam will support in such way when the exactly the same loading applied to the truss, and then that joint will move the same distance. So you will require, how can you design this one so they get the equivalent the support stiffness back to the truss. And then this is one task. And also once we understand how it works, and then we can maybe continue to work on, and then to model this one. Say if for example, if you understand the structure whatever you build under the truss, and then they provide support stiffness to the truss, you can even replace all these structures with a spring under it with a certain stiffness, and then this with this spring support, the structure will behave exactly the same as what you that model in the first stage with a column under.
So let's have a look at structures. How can we model these structures, these truss structures in Autodesk a little bit more efficiently? So to enable us to do it more efficiently, we better maybe have a look at the information what we got so far. So to summarize this one, I do a sketch in here. So what we got is got the Z direction, and Y is here as indicate in Autodesk Robot. So this is Y direction, so that is the X direction. So the truss structures is along, say from here to here, is 4 meters above the ground. So let me draw this outline of the structures out in here, and there will be a full base at 2.5 roughly here, and here, and here. Okay, so if you look at the X direction, what you're going to have is that each bay, these structures is going to be divided into two small pieces, and then you connect in the middle, so you get that secondary truss member in here. So the each bay originally is 2.5 meter, but because of this one, you need to divide this beam into segment. You need to draw from here to here, here to here. You cannot draw from here to here, because if you draw that way, this beam is actually not connect with these two. So to enable this connection in here, you have to separate the beams into two segments, and then so all the joints connect in here. So because of this, so you have 2.5 meter each bay in here. So in total you have 8 of them, so I don't draw them out one by one. So you have 8 of this 2.5 bay. So if you draw this one out, that if this is a line 1 grid line, and the line 2, and then this is going to be line 3, and so on, so on and so forth. So the last one 1, 2, 3, so going to be 9, because you get 8 bay in total, so 9 line. So in that direction, so you have the first line, which is ground floor, which is coming here. So let's use A to represent that one, and then the second line is going to be the bottom chord of the truss, so that's going to be the B axis. So the last one, because you want to snap into the middle point in here, so you have another that grid line, which is a C in here, and the final line is 6 meter above the ground, that's the D. Okay, so this is the grid line we need to generate from the structures in here. So let's have a look at the truss structure in the Autodesk Robot. Let's try to model it.
Before we start the structure modeling in the Autodesk Robot, let's have a look at the dimension information we got from the Word file we upload to the Moodle. And as you can see that the top core and bottom core are slightly larger, so they are 80 centimeter square. So what we're trying to do here, we give you a simplified version, and then so which means we are using a solid rectangular cross section area instead of using the hollow section, because normally that the truss use the hollow section, but it will make it more complicated for us to do the calculation later on. So to enable us to do this model more efficiently and then do the calculation later on, to demonstrate the idea, the methodology we are using in the later of this video, so we better maybe keep it simple, so everyone is solid rectangular cross section, and then the dimension is given in here, so 80. So let's assume you got the 80 by 100 millimeter square millimeter cross section, so will provide you 80. So for 40 square centimeter square, so we have a 50 millimeter times 80 millimeter, so that's the dimension in here. So for column that we got in there, so it's 100 by 100, so that's give you 100 centimeter that cross sections. So this is all the information we have, and then for the cross section, so what we can do is that then we can come back to the windscreen and then start to model this one in Autodesk Robot. So let's load up this Autodesk Robot, and then say let's renew a project. So when we model this one, we are not using the truss structures because we're going to put a column, and then we're going to put a beam in, and also because the beam support is going to be perpendicular to the plane, the truss structure plane. So that's why we need to do in here use use the frame 3D design this model to create these structures. So don't use this one, okay? Don't use the truss, otherwise it's not going to work, because you can later on apply that beam or columns properties to the structure we're going to add on. And then so let's use this one, the frame 3D design. So once created, and then there are several informations we would like you to maybe have a look. So these informations will include the material properties that we are going to use, we need to use later on. So let's assume all the structures we're going to create here is all steel, no matter truss, column, or the beam we create is all the steel structures. But we still would like to maybe have a look what is information we need. So the information we need is about the Young's modulus. So the Young's modulus of the structures can be found out from here. So you click Tools, and then goes to Job Reference. So click on Job Reference, and then after that you click on the materials in here, and then you can click on the modification. Will bring up the table, and then that you're interested in. So there were different type of steel, as we said, S275. Oh, sorry, here S275, S35, different type of steel. There do have that one. General steel structures which we use in the most of the finite element analysis structures. So in this type of structure, type of materials, you have a Young's modulus, which is important to us. Also, we have the other normal that property mechanical properties of the materials is listed in here. So you have Young Poisson ratio, shear modulus, and you have thermal expansions coefficients as well, so on and so forth. So we are mainly concerned on this one Young's modulus in here. So I'll write it down in the paper. So that Young's modulus is actually equal to E is equal to 2 0.5 and then 0.000 megapascal. Okay, so that's the Young's modulus I write on the paper already, and then I'm going to show you in a minute. So let's write it down, this information, so that's shown on the paper in here. So once you've done this one, so you can click on OK, and then this window been closed, and then you can click on cancel. So we didn't do anything, we didn't change anything, we just need the Young's modulus. So let's cancel these structures. So once ready, now we are ready to create the truss structures as indicated in the Word file upload to the Moodle. So first we would like to maybe create the actual line system, so allow you to draw these truss structures easily, and then because you can snap onto the intersections, so you can draw these truss structures that easily. So in X direction, as we said before, we start from position 0, and then numbers of repeat is identical. It's 8 of them. So each one is 2.5 meters. So once done, click on add. So you get all this one add-on line by line. And then Y direction, we only have one panel, so we don't need to create any additional grid system for the Y direction. So we only create one for Z direction. So Z direction, send again from ground floor is 0 meter. So the first one is from the ground floor to the top of the column. So let's make it one repeat is only. So that height is 4 meter as we indicate in the drawing. And then so after that, so what we're going to do is that we need to add on to the 2 bay for the truss system. But the truss system, because we need to draw the intersection that's separate the longer bar in the middle in the vertical direction, so the each bay is going to be 1 meter each. So we need to let's close this one. So we have a 2 repeat, and then each one is 1 meter. So once you click on add, and then that's going to complete the grid system. So once this done, you click on apply, and then you click on close, and so you got this grid system to allow you to draw the structure that step by step. So before we start, we need to select the members, again, create the members. So make it easy for us to do the demonstration, do the calculation later on. So we assume all these structures are solid rectangular cross section because it's easy for you to calculate. And then if you use a circular hollow section, and then which is commonly used in the practical project, and then the calculation will be much more complicated. You can need pi r square divided by pi d these things. So we don't want that. So we want a simple, straightforward to demonstrate this idea. So let's create elements, cross sections that will be rectangular solid sections, easy to calculate the cross section area. So to do that, let's use the bar sections which indicate in here. So you click bar sections, and then what I have done is, because I did a kind of a bit practice before, so I already create quite a few of them. So let me delete all these ones. So I just click delete all the sections, and then yes, so everything, maybe delete one by one, and delete again, and then so nothing there. Okay, you may have something on your screen, but that doesn't matter. So you can either delete it or leave it on, as long as you don't have the section I'm going to use, I'm going to define later on. So let's define the three type of the cross section. One is the top core and bottom core. The other one is the diagonal and the middle, the intermediate layer. So and then the final one is the column, the two column. So let's do this way. So let's create the bottom and top core. So what we can do is that in here we don't use the that standardized one, which is a I section, universal bin channel angles. We use the parametric, which you can manually that define the size yourself. So let's do this one. So top and the bottom chord, and then so top of cotton port, as we I should not double click. So the cross section we are using, the B as we said is 80. We have calculated this one. Pay attention to the unit is millimeter. Okay, and then the second one, the height is 100 millimeters, and because solid is a fill in the middle, so we take the solid and give a name is a top and bottom core. That means this cross section is for the top and bottom core. Now once done, you click on add, so you can see at background. So the top and bottom chord has been created in there. And again, we do the median one. So the middle cross section is 50 millimeter times 80 millimeter height, and then the thickness we don't need because it's solid, so take this one, and then name of it should be changed to the just double check. So so it will be the middle layer. So let's change the middle layer. Oh, I forgot to mention one thing. So even for the top or bottom core, the section type has to be steel. So we need to make sure this steel has been selected. Okay, and then I forgot to check for this one. So but doesn't matter. Let me do it this way. If I finish this one like a middle layer, I click on add. So you see the middle layer is add on there. So let's close this section, and then we can highlight the top and bottom core, double check whether we have that assigned steel that materials to this cross section already or not. So when you click on this one, and then you can use this section and the database, or using delete, or using this new. So what you can do is that you can click on the open this section. Oh no, sorry, double click. Sorry, I forgot. It's not using this one. This one will load that a new database for you, which has predefined the database for you. So we don't need that. So you just simply double click. So so I'll do it again. Close this window. So you highlight this one, and then so highlight, oh no, the highlight so before is select in this way, so you just need to highlight this one, and then after that double click, so we bring up the window again. So yes, we have set to the still as well, so you make sure if it's not if you set to RC bin before, then you need to bring it back to the still. So and then oh gosh, because we change it, so we need to redo this one again, so we need to put all these cross section, make sure 80/100, right? So 80/100, yes, correct. And then top and bottom core name no change, and solid, yeah, still correct. So if you click on add, he will check that it already exists. Do you want to modify it? You click on yes. But actually we didn't do anything because this is keep exactly the same as what we had before. So but this is just make sure that you double check the section type, the material has been set to still, otherwise it will be wrong cross section. So the last one, so is a column, so we need to click create the column section, CROSS cross, oh sorry, no, column, and then for the column, so this dimension is a square one, so so going to be 100 by 100, and it's a solid, and then make sure check is a still, and then click on add. So these three cross section has been created. So we're done. So after that we click on close, and then we done then this saved in the database already, so we can close these windows as well. And then we can start to draw this structure by activate the bar mode, join mode. So when you click on this icon and then bring up this window, and what we're going to do, so let's do this one, charts top and bottom first, and then we need to make sure we use the simple bar. The second one, the section, is going to be top and the bottom core. So the top core is pretty easy, because when you draw this one, we do have one that one bar, and then one bar vertically connect to here. So to make sure these two joints are connected, so you do need to break this one into two. So draw one line from here to here, and another line from here to here. So you get a joint in the between. So when this line connect to this part, these three bar are connect together, so they move together. The joint move together. We have talked this one in our lectures already. So because all the finite element simultaneous equation we create at the end is about the equilibriums around the joint in x and y direction. So you understand this one already. So that's why you need to separate this bin into two. So let's do this one one by one. So when you do this one, there was one interesting function I need to mention to you is a jack. So let's say I do it now to show you what the difference between jack and then jack ticked or unticked. So when you create a element without the jack mode, what you can do is you can click one line and then jack to the next one. So you create one single element. So then you continue to draw the other one. So you click on one line, the starting point, and then draw the next one. So you create the second one. Okay. So but if you activate the jack mode, you can see an interesting thing. See, you have a rubber line following you. You can click on here to draw this one, and then here to draw the second, and continually you can finish all this one. It's easier. So when you press the ESC key at this mode, when the drag mode enabled, it will temporarily how to call them, disable the rubber line. Then you can restart at some point to draw this one continuously and then in the next maybe segment or next column line. So we done the top core. The bottom core, when you look at the joint, you will see that the joint, which I'm going to bring back to you. So you see the joint here. So the joint here is that connecting one to the end here. There was no bar connect in the middle that between F and joint F and joint G. So the kind of important thing is when you draw this line, it's better not to draw F to middle point and then middle point to G, because if this is a single bar without any line connect from the other direction, and then you put a hinge there, this is actually unstable structures. So we don't want that in our analysis. It's better for the bottom core, if you don't have anything in between connect to this bar, so it's better draw a single bar from joint F to joint G. No, it's not better, it's you must draw that a single bar from the joint F to joint G. Okay, let's come back to this one and then continue our job. So let's start from this point again and then continue to the next one. So, and then from this part, and then not here but the next one, and then next one, and next one, and then that's finished. And then once finished, you press ESC key, and then that's disable the rubber line. And the next things what we need to do is that we want to draw the vertical line. So we draw the vertical line in here. Okay, so we draw the vertical line, that's the median layer, so we need to change the cross section to the median the middle layer. So to draw this middle layer, and then we better, because you draw every time and then you need to start again from this point to this point, so better to disable the drag that mode. And so we draw the vertical bar first. So again will be this line to this line, and then this line to this line, this line to this line, this one and to this one, finally this one. Now the diagonal one, so vertical down, so let's do the diagonal one is going to, let's do the longer diagonal first. It's going to be from here to here, here to here, because you do have a connection in between, so otherwise this bar won't connect into the other two. So that's why we need to draw from here to here, and then another one from here to here. Okay, from this one will be the same from here to here and here to here. Okay, let's continue. One to here, and then, oh sorry, this is a mistake, so we get rid of this one later on, so let's leave it on. So let's start from here to here, here to here, and then here to here, and here to here. Okay, oh actually it's not wrong. Yeah, it's actually, we do have this bar, but we draw in different sequence. So but anyhow, I can also show you that how can I delete this one. Okay, so if you do make a mistake, this is not exist, but now this one is the one we want, but I just want to demonstrate how we delete this one and then to you. So to delete this one is pretty easy. You need to switch from the join mode to the select mode. So the easiest way at this mode, and then you can press the ESC key again, or you simply click on close of this window and then say both are okay. So let's do this one. Press the ESC key first. So if you move your cursors in here, press ESC key, and then this window gone, and then that bring back to the join mode. So then you can select and then press the delete key, and then that will delete this one. And then then you click on any white area, you can unselect this one. So I demonstrate this one again. If you have this window, you can also close this window by click on. So now it's join mode. Remember, when in join mode, you click anything, any place, he will start to draw a line there. So we don't want that. So that's why we need to close the join mode and then switch to the selecting mode. So let's close this window. So that's also bring back to the sensing. Okay, and also one important thing is when you have this one ticked, and then remember, if you this ticked and then you put your cursor here, you press ESC key, he also bring back to this part. And then sometimes if you highlight this one tick, and then this one, he will, oh sorry, it's also disappeared as well. So once this one disappears, so oh, I was thinking if I untick this one, I press ESC key, it won't disappear, but actually it's disappeared. But anyway, so anyhow, if this window is there, enjoy mode, press ASC key back to the selection mode, and then or close the window back to selection mode, and then select this bar and then click on delete, and then this bar has been deleted. Okay, and then so now we've done the diagonal, and then let's start to continue to draw this diagonal in here. So let's do this one by one. So connect this one to here, this one to here, this secondary member. So this part we just did it, but actually we should have. And then one bar in here, one bar in here. Okay, so also we can draw a vertical line, vertical line, vertical line, and this short secondary trusses. So now this truss has done. So the next one, what I'm trying to do is that I'm trying to maybe draw the column. So to draw the column, so what you can do is that you can simply click on the cross section in here and change this one to column, and then but this time this is not simple bar anymore, it's going to be a column, and then make sure you select the column like this. So and then you can draw the column by click on this line and then down to the bottom, and then this line down to the bottom. So this two column has finished. So once finished, you close the window, and then this is actually the line diagram we create for the analysis. If you really want to see that the structure in 3D section mode, what you can do is that you can move your cursor to this one, this small icon here, set section shapes, and then click on second shape. So he bring back the size of the column and show on here. So if you hold on your shift key and use the scroll buttons in your mice, and then you can spin and then see the structures. So you can zoom in to have a look at how these structures looks like that from different angles. So once done, if you're satisfied with your structures, you click on this button view, and then click on the XZ, and that structures, and then back to the model that the front view that we got before. So the next thing I'm quite quite interesting to show you about the stabilities of the structure, because this is a 3D model, but we can create that one that 2D panels in this one. So theoretically, these structures is not stable. Say for example, the structure out of plane in y direction, so along the y direction, and then if anything touch this one, so although we don't have any loading applied to this one, but this structure could easily fall down. And then if you not have any restraint of the structure in y direction, so y is unstable. So y is unstable. So let me move a little bit to this one. So if one is unstable, and then what we're trying to do is we need to that the model a little bit the structure in here. Say for example, normally the structure at this joint. So when the column connect to the truss, so normally they will have a hinge connection. So supported by a hinge that from the column head and then connect to the truss. So if you want to do this the hinge connection, which we have maybe practiced in the other examples already, we use that release to do this one. So let me demonstrate how we do that one for you, and then after that we continue to show you what is the correct way of doing this one instead of just release it. So let's say if we click on this one, I may use the release before, right? So you click on release, and then say what you have the fixed pin release or pin fix release, and then pin release in here. So which I already generate. So let me have a look at the pin release. If you use a pin release, which means you click on here and then both are released done. So this release, and that's not what we want, because we only want to release this end, so we'll be only in one end. So let's delete this one. So let's delete the bar release by choose this delete bar release, and then come back here, you click on this bar, so this tool release has been removed. And then the fixed end release and then a pin fixed release is only one end release. So but I don't know which one is the starting point with end point, so but I can have a try. So I highlight this one. So if I click on here, and then this is not what we want, so we'll be possibly we need to use another one, pin fixed release. So this possibly starting point. So what we do, and then you come back again to delete this one. So you click on here, so delete this one. So it's not this one. So we use a pin fixed. So let's highlight this one, and then you click this bar again, and then this time you got the release in here. So you can got the release at this end as well. So now since we have done this one, so colon with a pin release in here, but however, don't forget this moment we got trouble because let's have a look at this structure. So what we release, release the starting point where we draw the structure, the column from this point to this point. So the starting point, head of the column, you have a 3 direction release. Is it going to stable structures? Not. No, I don't think so, because the truss, if you get a hinge at that top, you can see that he can easily fall down in Z direction, in Y direction. So right, so it's like an unstable structure because it can rotate along this axis, which is x-axis, along this line from this point to this point. It's like a mechanism. It's like a hinge. It's like a door. It's closed. It's rotating. He can't stable the structures. So this is definitely not what we want. So actually we need to create a special release for this case. And then how to do that? Let's delete this one because this is not correct one. So we just do a demonstration how we do. So I can delete this one by click on this bar and then click on this bar again, delete it. And then once deleted, this is my release that we should use, but I created before. But make it that easy for you to follow, I delete this one. So just for you to see then how I create from scratch, from new one. So if you got this connection already, let's click on the new release. So you get a new release in here. So you got the new release for this structure. You can see that the release you have a starting point, you have end point, and then which one you want to release, you release the ux, uy, uz. This is this is the displacement in x, y, and z. This is rotatory equilibriums that you have from both ends. So what we should have the release in here. So we already know that this is the begin point. So end point we don't want to do anything. So the end point just untick everything. So everything in the z direction, you don't need to do any. Then for the starting point, we have to be careful. And then for starting point, let's analysis what the direction I should release then. So the rotation for this one, as we know that, so we should not release we should not release the along this direction, this bottom chord, this direction. So this is actually the x direction. So anything in along the rx should not be released. Otherwise, this structure, as we said, the structure going to fall down that the outer plane direction. So he may be that move the bend down and rotating about this axis. So this is not correct way. So we need to fix this structure along the x direction, So along the x axis. So all the rotation about the x axis need to be fixed instead of release. So how about the rz direction? So rz means these structures about this axis. So about this vertical, the column axis of this one. For this part, yes, we do need to release, but of course, no matter you release it or not release it, these structures is going to be the oh sorry, the Z direction we should not release it. Sorry about the Z direction is not going to be released, because otherwise this can be spin like this one along this direction, so we don't want to release. So this one should be connect to this one along the Z, along the about the Z axis. Okay, and then the Y is the one we need to release, so we untick the RZ. So Y is the direction we want to release, because the Y direction is about this direction. So when this structure bend down like that, we don't want this column rotate together with that, because there was a hinge in there. So we need to release the RZ. So once it's done, so you can give an entry some mild release, or maybe you can call it a wide release. Okay, so once it's done, you click on add, and then you can have a look at this one. So wide release has been added to there. So we do need to use the wide release to generate this one in here. So we highlight the wide release, and then you can move to the charge the bar in here. You click on this one, so this structure will be released in the XY direction, and then also you can put a 1 in here, so this been that apply to the Y directions as well. So this one will be released in Y direction, so along this the Y axis. And so once this structure done, and then we should maybe apply the boundary condition to this one. So this one done, so let's close the release and then close these structures. So the next one we should apply the support to the structure. This is boundary condition, and then the support boundary condition we should really use a fix to fix these structures at bottom. So we put the fix in here, we put another fix in here. So this structure has been created. So and then that structure done. So everything we need is finished. And then so what we need to do, have a look at the structure in the front view. So let's click on view and click on this XY front view, and then that bring back our working platform, so you can see this structure clearly. So the last thing we need to do is put the loading on. So to put loading on, the first we need to create the load types. So as we said, it's only one load case we want to create, make it simple. So we create a dead load only. So this is called dead load 1. So you can change the unnamed if you need. So we just click on add. So this structure, so this load type has been created, and then you close this one, and then you actually define the loads for the bin in here. So how can we do? So we can create the node force that apply in here. So let's say the first one, as we discuss in here, this middle node, every node top core, they have let me bring back the screen. Yeah, they have 71.4 kilonewtons that apply to the edge point, so in here, and then half at the edge one. So let's apply this loading. So the first one, we click on the node force, and then this time this force is going to be minus 71.4. In Z direction is minus, okay, it's downwards. So once you click on this one, you click on add, and then after that you can come back to the structure in here, but make sure you highlight this one. And then click on apply, and then so you highlight this one, click on apply, then you come back to the model window. You will see that your cursor has changed to this applying mode for applying the node to the join. So let's click on this one. So you got the first node, first force point force on, and then click on second, third, fourth, and then all this one has the proper loading on. And then after that, you need to change this density, the loading, to which is a 75.7, because it's half of it. So you click on add, and then apply to the, if sometimes this one disappeared, then you just need to make sure you click on the apply, and then that's going to bring back your applying mode. So you can apply node 1 and node 9 in there. So once this done, if you're interested, so that you can close the window. So this structure basically is finished. So if you want to have a look at how much loading apply to the load value, so you can actually click on this button. So this button here. So maybe they didn't show you the window here. Let me close this window first and then come back to load definition. So that's bring back the loading, which for the dead load case 1, and then so if in that case, in that model, when this one activate, so you move to your cursor to here and click on this one, that show you each value of the force you apply. So you can double check if you make mistake or not. If you're not if you confidence on data, so you can untick this one and close this window, and then you can start to run the analysis. You can go to analysis and calculate. So it's done, the structure. So once done the structures, what we can do is that we can go to the result mode, and then you can come to the results, and that bring back this window in here. You can also see the deformation by click on this one, and then so you can see, okay, so this is the structure after deformed, what it looks like. And then you can also click on, if you connect select the deformation, and then you can start an animation that show you how this loading develop that one by one. And then so maybe take a while. Yes, that window bring back in here already. So from here, so you can run this video. Oh, why it can't run? Oh, another one. Oh, should be wrong. Okay. Anyway, this is if you want to see again, that's the video that's generated in here, and I can't remember how to do that dynamic view for this one already, but it doesn't matter. But the most important that we get the result properly. So once we done this one, and then we close this window, so that gives you the deformed shape, and then you can enable the deformed shape, or the original or disactivate by click on this one. So this one will come back to the original structure, and then click again to give the deformed shape. So if you done this information, what we're looking for is later on, one thing was very interesting that I'd like you to focus on is the number 14. So number 14, if you don't know which node that we are looking at this one, you can also come to this point, click on the node number, so bring back the node number for you. So this is 14 node. So we're interesting to see top of the column, and then how much this deformation is going to be. So to find this one, so what we can do is that you can click on the tables, and then select this not reaction. So let's deselect the reaction. We don't need the reaction. We need the nodal displacement. Nodal displacement. Click on this one, and so once you bring up, oh, this may be on the back. So let's have a look. It's the back in here. So you see the 14s at low case 1, and the deformation at the z direction is -1. It's quite interesting number, -1 millimeter. So this is -1 millimeters that for these structures. I'm writing down this one in a paper, so you won't see me, but I do get a pen and writing down here. So the results of this one and is the node 14 and then UZ direction is equal to -1 millimeters for these structures. So that's all the analysis that we need to do. So the next one, what we want you to do is that I say, for example, got say, or maybe you, not me. Okay, you got a job from the clients that he want to take out the column because the column may be in the middle of somewhere. He want to create a opening space, like a 6-meter opening space for a shop, that front gate, or maybe for living rooms in a residential building to create a bigger space. So to do that one, you do need to put a steel bin. Say, let me rotate this structure. So put this bin in here. Oh, make it easy to view. Let's come back to the structure mode and then start, and then so let's come back to this one, and then I don't need this node, so let me disable the node, and then I draw this and rotate this one a little bit in here. Say, for example, between here the clients need a 6-meter opening space, so this column need to be removed and then to replace by that a beam from this end 3 meter away, connect to another one 3 meter away from here. So connecting this one, supporting this truss. So what this structural engineer requires to do is that the stiffness of the bin you put in should have exactly the same stiffness of the column. So in another words, which means if you apply the loading on the top of the truss, top core, if this joint moved 1 millimeter down, so the new bin come in to support this truss, they should deform under the same loading exactly the same 1 millimeter as well. Say for example, this structure, they may have a link to a glass roof or facade, or somehow they have very sensitive displacement requirements, and then which not allow you to put in any stiffness. They has to deform like that. So how can we do that? How can we find out this? How can we draw such bin and then construct such bin that provide this that stiffness for this truss? So let's have a look at the sketch we have created, and then discuss this one that before we actually put our hands on to modify these structures. Okay, let's have a look at the information we got, and then try to decide that the bin which are going to give exactly the same support stiffness back to the truss. So, and then this is the data spreadsheet I just record. This gives the dimension of different cross section in the truss and column, and that's the Young's modulus for the steel, the materials the only materials we used in this demonstration. And then that's the deformation of the head of the column and along the Z direction, and then that was the 1 millimeter downwards. So let's put this aside, and then we're going to maybe focus on the design of the structures. So before we do that, let me summarize what we got so far, and also try to design a conceptual design of the new structure we're going to do. And so this is a truss, okay, and then with a column supported, and on the right hand side, this column is going to be removed. Originally this column was supported by the column, support by the ground, and then a P loading was given by the truss, and then on the top of the column, and the total height of this column is 4 meter, and then we use this one, the L column, to represent this length, and so the loading is P applied in these structures, And as we know before, the stiffness of the column, K of the column, should equal to the P, the loading you apply, and divided by the delta, the deformation, the head of column deformed. They should equal to exactly the Young's modulus of the column and times the EA with the area of the column divided by the length of the column. Basically, it's a EA over L, right? So that's the stiffness of these structures in vertical direction. And then the new structure we're going to create is like this. You have a truss in here, and left hand side connected. Left hand side connected, no change at all. But right hand side is going to be removed. The column been removed. So I isolate this column and the beam, and then showing it here. So that's the size of the beam, and then going to support. Assume simply support by some other structures on wall or on some of the other columns that in 6 meter distance that apart. So this is a 6 meter, and then which we're going to use the L beam to represent the length of the beam. And so with the loading P, exactly the same loading P given by the truss applied in the middle, and then this beam is going to be deformed that a delta distance. We use this capital delta to represent that one. So the delta from the second year study using the Macaulay method, we already proved that this should equal to the P L. L is the length of the beam, and then divide by 48 E I. I is the secondary moment of area for the beam, and then that's information is linked with the size of the beam. So that's what we're looking for. We want to know what the size of the beam is going to give you the exactly same stiffness that vertically at this point that as the column column has. And so let's do that analysis later on to find out the stiffness of the beam at this point first. So the stiffness vertically, if you put a P loading on this one, if you want to calculate this support stiffness of this one, I suppose to use the K of the beam at that moment should equal to what the loading you got divided by the deformation you achieved. So that's actually the stiffness of the beam supporting the truss. So this should equal to, and then 40A EI of the beam, and divide by the length of the beam and cubic, right? So because you are looking for exactly the same stiffness, support stiffness from the column and truss, so these two should equal to each other. So if these two equal to each other, so what we get in here is that the EA colon divided by L colon should equal to the 40A EI beam divided by the L cubic of the beam, the length of the beam. So we are looking for this one, okay, IBM. So the I of the beam should equal to area of the column. Oh, sorry. Before do that, I should mention one thing: is that the reason we use the same materials is because in this case, it's all the structures built by the steel. So the Young's modulus is going to be the same. So we just need to cancel it straight on, and then make it such a simple way of demonstrate the samples. Otherwise, you get a different E than more complicated situation. Now, so A colon, so let's continue this deriving. So times the L length of the beam cubic and divide by the L colon and times 40A. So once you done that one, you put a number in. So A colon is 100 centimeter, convert to millimeter is this number here, and times 6,000 millimeter cubic divided by the length of the bin is the 4,000 millimeter times 48. So you pay attention to the unit. So square times cubic give you 5 power 5 divided by millimeter give you millimeter power 4. That's exactly the dimension. The units should be for the secondary moment of area. And so let's do a calculation. Let's use a calculator to do this calculation in here. So what we have 100 centimeter, now millimeter square, times 6,000 times 6,000 and times 6,000. Stupid way to do. And divide by 4,000 divided by 48. So that's the number we should have. Okay. Yep, that's the number we have. So that should equal to 1.125 times 10 power 10 millimeter power 4. So once we get this one, then you can either design a circular beam, design a triangular beam, design any shape you like, as long as they give this stiffness. So this second moment of area, this bin stiffness going to be exactly the same of the column. So the secondary moment area of the structures can be different if you use a different cross section. The simplest one, I think, so far is still the rectangular one. So if we use a rectangular beam and then you have two parameters to decide, you need to decide the breadth of the beam and the height of the beam. So to create a beam, breadth and a B and H of the bin, given this number, so what we can do is that we can assume this one, give a try, and then this one, assume this is a 400 millimeter first, and let's figure out how much the H going to be. So what we have is that the I and then of the bin, second moment area of the bin, should equal to the BH cubic divided by 12. So that should equal to 400 millimeter, 400 millimeter, and then times the H, which is the one we're looking for, and divide by 12. And then so that should equal to the 1.125 times the 10 power 10 millimeter power 4. So the H should equal to then will be 12 times the 1.125 times 10 power 10 divided by 400 and cubic root in here. So if you use a calculator to do the calculation, that should be this one times the 12 and divide by 400, and then so that's equal to this number. I don't want to write it down so too complicated and too long, so just exactly cubic root. So that's equal to 696.238 millimeter. Okay, so the H now can be decided. Now is should be equal to this number in here. Okay, once we got this one, then let's have a try. Let's give a try in the Autodesk robot to model this structure, to modify structures in here, and then with bin support that the cross section 400 wide, and then the 696. This one can be ignored to around 700 height. So let's try to do this one in our Autodesk robot model we just create. Do a little bit modification to that one. Okay. Okay, now we have got the size of the bin, which will give exactly the same support stiffness back to the truss. So now we are ready to construct this bin. So let's have a look at how we do this one. So you trying to rotate this bin to a proper direction, which allow you to see the right hand that column easily. So, and then also you're in the selecting mode. Let's maybe select this beam, select this column. This column going to be removed, so you press the delete key. So this kind of the Robert software will pop up a window to ask you, I really want to do it. Yes, you click yes, I got to remove that beam. And also you can delete the columns, the foundation as well, by click on delete key, so that's disappear as well, because then if you want to create open space, that's the open space, people can come in through there, so, or open in living space as well. So once it's removed, we need to construct the two support bin. The two support bin will be 3 meter here and then 3 meter here, two segment of this one 6 meter long beam. And then you can either draw this one, or the other way you can actually use the tables to generate this one. So let me show you how to do. So we know this one, the coordinates of this one is 14. Sorry, it's a no 14s already, right? So we already that check this one before is a no 14, and then the new node we're going to create is one node here. So the new node, the x coordinates is going to be 20 meter, and then z coordinates is going to be exactly 4 meter above, and then the y coordinates will be along the negative 3 meter from here, and then the other node will be the y will be the 3 meters that in y positive direction. So once we got this one, let's go to the nodes, and then we can bring up this node table. So that's node number 14. So we're going to create two new node. So let me click on here. So what we're going to do is that we're going to create this new node. The first one is the x direction 20 meter that in x, and y direction is going to be negative 3 meter, and then oh sorry, that's going to be wrong, so because that's going to be 20 meter, and that's going to be, because the dimension is in meter, pay attention to that. So going to be 3 meters that on this side, and then z direction is going to be the 4 meter high. So once this done, if you press enter, this node is created in here. So these two are the first segment of the bin. And then so the next one is going to be, the coordinates is going to be 20 meter again, and then the y coordinate is going to be 3 meter, and then the height is 4 meter. So these two, once done, you press enter. So this two is created. So will be 20, 21. So the beam we're going to create is linking the 20 to 14, 14 to 21 as well. So we can use the same table to do that one as well. So what we're trying to do in here, you can use the bar table. So, and then when you use the bar table to create this one, so make sure that you set up this bin for this one in here. The first one is 20 to 14, so we choose 20, node 20, connect to 14. So give you this one, and then dimension of this one. Oh gosh, we forgot to create the dimension, cross section dimension for this one. So we're going to leave this bin there. So let's do this one. So let's close this window, and then not be able to close. So let's come back to start first. So leave it that on. So this bin is created, but no dimension at the moment because we forgot to create this cross section for this one. So we need to come back here, click on bar section, and now we're back to this screen. So we create another new cross section, which is going to be the beam for this part. So the dimension, as we said before, is going to be 400, and then the height of this one is the 696 and 0.238 millimeter, and then solid section, and then you click on add. So this structure is going to be add to that one. So once that done, and then you can close the window and then close the window. And so as we said, this one hasn't been assigned a cross section yet. You can do either way. You can do going to use the bar element, and then you can change this one in the spreadsheet in here. So if you change this one to it's not there, bin cable 1. Why is cable 1? I should have a bin. Let me check. So let's come back here. So maybe some mistake in here. Let me check. We do have bin here. What's wrong with this one? Let me do this way. So I select the bar, and this one should be a beam. Let me do this one again. So I say, for example, I key in 20, and then key in 14 again, 14 again, and then choose okay. So that's now this time this structure update. So maybe when we have this window, until we change this one, he not update this structure. So let's do a little bit change in here. So then you can select the bin. So you see, once you change it to bin, and then you close, and then also need to make sure this one is going to be the steel or S275, or you can use S275. Will be the same of the steel bin. So once you choose this S275 or steel, because the Young's modulus should be the same, and then once you close this one, before you close this one, you see this bin has been changed already in here, right? So you can either use this way to do that one. So let's come back to start, and then you see this bin has been created. One section of it is created already. And the other way you can do is that you see this small node there. You can use this bar to create this one. And also another way to assign the section if you forgot. So you can do in this way. Let me reverse this one. So I get the bar in here. Let's pretend that we haven't applied the cross section to this one. If I close this one, and then this one come back to the cross section that without the assign. So if you got to this point, say like this structure without that cross section being assigned, you can do in this way. You can click on bar section, and then you can highlight the bin, and then you can come back to this one and then assign to this one, and then yes, and then we'll do the same job. So either way will be fine. Anyway, so let's close this one. So the next one, to link this one to here, we can do the other way. You can use this bar section to do it. So then you can click on these structures, and then you make sure you choose this one to beam, and then change this one to beam as well, the section. And then once you come back, you start to draw the node from here and then to here. So that's create the same beam as well. Okay, so once this done, and then you close this one. So structure has been rebuilt. So this is the new structures, and then with the template support bin. Now you've got a 6 meter opening for your maybe your shop front, or maybe your living room, the large open plan living room as well. So after that, we need to apply to the support to these two structures. So we click on this one, use a support, and then this time we use a pin, and then you come back to apply the pin to this one and pin to the other end as well. So once done, close this one. So we can rotate and have a look at the structures in here. Okay, so this is pretty nicely done. So once done, and then you can run the analysis. So you can run the analysis by calculate, and nothing wrong. And so you can go to the result, and then result in here. And if you want to see the deformation, you can click on this one. So you can see the deformation looks like this one. Okay, so if you want to find out the vertical deformation of 14, we do the same thing. We use a table in here. Click on tables, and then bring back the node displacement. So let's take the nodal displacement and click on OK. So check 14, the deformation exactly -1 millimeter. Okay, we did it. So there we did it. We got it now. So the next one, what I'm going to do is that I'm going to continue to show you. Say, for example, if I just want to create the mathematical model, and then which has a one spring support under this one to replace the column, and then as long as I can set this spring stiffness in a right that amount, the right stiffness, so you can get exactly the deformation as column support as well. So let's demonstrate how can we achieve that then in next stage. So now our next task is trying to find out that a spring that which has equivalent stiffness of the column. So and then we replace the column with spring support directly. And although this is not a real structure, but just for the concept of structural modeling, and then how can we achieve that? That before we do that, I need to kind of bring back this information in here. Okay, so the column stiffness is equal to the EA column times the L column. So let's have a look at the deriving in here. So I put this aside in here and trying to figure out how can we get the spring stiffness out from here. So as we set this column 4 meter high with a P loading in here. So the K column, the stiffness of column should equal to P over delta, and should equal to E times the A column and divide by L column. Okay, so which means that should equal to the Young's modulus of the column, which we have recorded down in the previous data sheet. Let me figure out where it is. So that should equal to, as you can see in here, is a 205 megapascals in here. So this 205 megapascal we need to convert into in all our stiffness in here. So we're going to use the kilonewton meter as a unit for this one. So the Young's modulus is a 205. Put it back in here. 205 000 that megapascal. So it is a times power 6. And then Newton per meter square. So that's the Young's modulus you have at the moment. So we need to convert into kilonewton. So that should equal to the 205,000 times 10 power 3 kilonewton, and that per meter square. Okay, so that's the Young's modulus we have. So this should equal to the 205,000 times 10 power 3 and times the area of these structures is equal to the 100 centimeter. So 100 centimeter is actually equal to the 0 point. So it's 100. So what we used before, let's say if it's 100 millimeter is equal 100 centimeter, this one is that 100 centimeter by 100 centimeter is actually 0.1 times 0.1, or if you want to convert 100 centimeter to meter square, so that should equal to the 0.1 0.1 times 0.1 that meter square in here. So actually this one should equal to, if you convert directly, 0.01 that meter square, and divide by the length of the bin is 4 meters. So once you've done this one, let's use a calculator to figure out what this number should be. So this is equal to 205,000 times that 1,000 10 power 3 and 10 power 3, and then times 0.01 and divide by 4 meter. So that's equal to the 5125 00 kilonewton per meter. And forgot to write out the unit for the Young's modulus. This one we should put in here. That should equal to the as we said, is kilonewton per meter square. Okay, so that's what we should have for this one. So this is number, the stiffness K, we should put into the model, and then we should have exactly the same height of the structures. So let's switch back to the Autodesk robot, trying to work out these numbers, and then with this work out the numbers to create the spring under the truss. So let's come back to the robot. Okay, so now this is the model we have done before. So we're going to remove these bins and replace by a spring of the structure. So how can we do that? So let's come back to the structure model and then select the start. So once we come back to this one, we need to remove this displacement from this one to make it look nicer. And also let's remove this support, and then by delete this one, and then yes, and then delete the other one, yes, and remove these two support, and remove this one, remove it, click this join and delete this one as well. Okay, so all this structure has been deleted, and then we're going to create the a spring support to the structure. So what we can do, we can directly use the support, and then this time what I'm going to do is that I'm going to create a new support. So this new support, as you can see in here, instead of use the rigid informations in here, I'm going to use an elastic. So the elastic, which means I need to define which direction I want to fix and which direction I need to connect with the support. So because this one, let's assume this is a pin support in this direction. So we basically going to fix the, we're going to design these three. So let me untick these three. So if I put support of these structures that which is in the Z direction. So say for example the Z direction, I'm doing this one at this moment. So this Z direction, I'm using the elastic coefficient, and then this coefficient which we got from previous the analysis is equal to the 5125 kilonewton per meter. This stiffness we want to put in here already, and then these three directions, what we do need to fix is to fix the rotation rotation y, because we fixed the rotation y, so these structures are not going to be able to rotate in y direction. So rotate in y direction in here. So we're going to fix this one. So this not fell down in y direction, and also not y. I'm sorry. So should be the x direction as we mentioned before. So it's about this charge not going to rotate along the x direction. So we're going to fix this one. So this one don't fall down to y direction. So this one not fail to this direction, not fail to this direction. Okay, so this Rx need to be fixed, and then Ry we don't do anything, so this is going to be released. Rz is going to be released as well, and then also to prevent these structures to move on y direction, I also need to fix the direction in the y direction. The uy is not going to move, but I set the x direction free, so x direction can be moved freely along this direction. So it's like a roller put on this side, so the x direction not restrained, and then the y direction, the horizontal direction, the movement is not going to be allowed. So this joint not is fixed in this direction, it cannot move along the y. And rotation, we not allow this truss to rotate about the x-axis, so this one should be fixed. And then this direction, z direction, is a spring. So once we done this one, you click on add. So we put this one to a spring support, spring spring support, to this one in here, and then you click on add. So the spring support is add to these options. So we close this window, and then we just need to highlight this one, and then we go to this joint 14 and click on this one. So you can see this one has been that apply to these structures already. So once done, you close this window, and then you can have a look at the details of this support in here. Okay, to see it more clearly, and then you can also do in this way, so that you can remove this section in here, so you can see this structure. So let's zoom in a little bit and then see. So this one representing this one, the spring, representing the spring. So this one fix the y direction, so this one cannot move along the y direction. So this square in here means this structure not rotating about the x axis. So once this done, and then we can actually start our analysis as well. So let's do the analysis. So you go to analysis, calculate. So the structure is finished, and then after that you can click on the deformation. You can see the deformation is quite similar to what you have before. So if we go to the result and then see this structure in there, and then also if you bring back the window in here and choose the node displacement and click on OK, check the number 14, the deformation is exactly the -1 that the deformation you got before. Okay, so that's all the demonstration I want to do. Hopefully that helps you to understand the support stiffness, and then how you model the structure differently, and then get the understand of the spring support that we have in the Autodesk Loper. Hope you enjoyed the video. Thank you so much. Bye bye.